Good afternoon. So welcome to the afternoon session of today's GAN program. We have with us Professor Debojyoti Ghoshal from Jadavpur University. Professor Ghoshal is an expert on crystallography and total and organic frameworks and organic framework systems. So today he will be talking about in the class about exostructure, a Pathfinder way of chemical science. And this will, I hope, you have seen this nice lecture of Kari in the morning with structure analysis, and I hope you will find applications in his talk. So with this, I request Professor Ghoshal to please deliver the lecture. Thank you.
Okay. So, perhaps at the beginning or outset, I must say you already had a lot of doses of crystallography and you are become expert of this subject. So, don't consider me as an expert, just look at me like experience what we have gathered to work with exocrystallography in doing something related to the synthetic chemistry, right? So, being the title of this talk is clearly representing that exocrystal structure is not only the mode for the characterization of the substance, but how it can instigate several new ideas, the path of new thinking, what are not very commensurate with the previous idea and the textbook ideas we have, right? So it will always give you a better chance to think in a new direction. So that will be the modalities of the talk. So let us start with. So what is exocrystallography? You know much about this. This is X-ray, which is an electromagnetic radiation, and electron is also being a electromagnetic radiation. It interacts with X-ray and diffracts its beam in several directions. And the exocrystallographer, like you people, what you have tried to make in last couple of days, the crystallographer can understand the diffraction pattern, and from some mathematical calculation and understanding of fundamental physics, you can understand the structures, right? But how was the journey was? If we like to see the origin of this particular topic, that was come much before the invention of the X-ray, right? Do you know this person? Anybody? Obviously, not any relation with this. He is Louis Pasteur. So, what he did is his PhD thesis was on the separation of optical isomer of tartaric acid. You know that tartaric acid have D and L form, and you heard about this story that when the tartaric acid is extracted from the tamarind, it has a separate optical rotation. When it is synthesized, it has separate. So now we know that these are due to the D and L form. But what Pasteur did, he first separated by hand and tweezer the two different crystals of tartaric acids, right? So this was his PhD dissertation work. So this indicates that the internal structure have some correlation with the external structure, and that was the when crystallography has invented and studied a lot, then people realized that the Pasteur's work have an implication over this way of thinking, because this was the first method. People who have studied stereochemistry, at the beginning you will see only two lines is written. That is the separation of optical isomer by hand and tweezer methods. This is the understanding that from the external structure, you can differentiate the internal differences of the structures. That means the D and L form, which have the separate orientation internally looks different in external pattern as well, right? So these are the crystals, beautiful, right? What is coming in my mind about the crystals, not the Bragg's equation and other things. This looks very beautiful, particularly when it comes with the transition metals. Colorful, nice, shiny. But if you look internally, the situation of the atom or the orientation of the atoms are ordered in the crystals, right? As you can see, the people are standing here in an ordered pattern. But the same entities, like the same atoms, if they are organized in a disordered pattern, that are not generally meant as crystals, right? So this is a picture. These are the same species, Homo sapiens, right? Organized in a particular pattern here, but this is a picture of Shialda railway station, sometimes in around 10 o'clock. So these are the same species organized in that way. This is the difference between the ordered and the disordered. So in crystals, the atoms are oriented in ordered fashion. Why? Probably there is always a necessity of driving force. The driving force for these guys are the salary and the perks and what retirement benefit, what they are getting in joining the forces, right? So that's why this driving force make them ordered. There is no driving force. If you impose some driving force here also, you can make them this disordered atom ordered, right? So this is somehow related to the organization or the formation of the crystals. You need to force the atoms with some driving force to make them ordered so that you can generate the crystals. Sometimes these are, reversible, because here you can see our students at Jadavpur University enjoying the fest, and the same morning, the same people coming into the class. So that's why this system is reversible. So the same people can stay disorganized, but can also be ordered as well. But this system cannot be, reversible, right? Because if you say something in the railway station, yeah, order, make the ordered arrangement, nobody will listen to you, right? So some systems are reversible, some systems are not. So this is the bottom line story of forming the crystals for X-ray diffraction. So the story started with Röntgen. When he discovered X-ray in 1895, he never knew that, probably never knew that in next 100 years that will change the overall scenario of the structural science, right? So he was happy to see, the patterns of bones and its the power of penetration, etc., etc. But the story started with Max von Laue. Probably you heard a lot about this scientist in this course of classes. Max von Laue first invented the method of diffraction patterns, and he understood that the diffraction patterns of different systems have different types, and from the diffraction patterns with some analysis you can understand the nature of the atomic arrangements within a particular molecule. So just after 10-12 years of the invention of X-ray, the uses of X-ray just changes its gear to use into a new domain which was already not very explored at that particular point of time. And with the work of Laue, this particular field opened up like anything, and this is the Laue's experiment published in this particular literature. where he analyzed the shape of this zinc blade, and this was his experimental setup, completely handmade. There was no tailor-made X-ray crystallographic instrument, X-ray diffractometer rather. Our X-ray source, lead screens, crystals, and then photographic plate. So by analyzing the spots in the photographic plate, because X-ray, before the invention of the detector, people used to handle the X-ray spots with the photographic plates only. By analyzing these photographic plates, lots of calculations, lots of time, lots of understanding, he realized something related to the structure of the zinc blade. Now, a more quantitative way. The father and son, probably very much known to you in last few days particularly, they are connected with this equation. So, more quantitative way to the understanding of the Lawrence work. And that's why in 2 consecutive years, this batch of people awarded Nobel Prize, which is considered as a master achievement in science. Right? In 1915, father and son awarded the Nobel Prize. But the interesting thing, what I like to share with you, that this is William. This is Father Bragg. You can see, you can understand from the picture. And this is a picture of Lawrence Bragg. Lawrence Bragg was only 23 at that time. And he was, if you see the Nobel citation also, the theoretical understanding is counted for the Lawrence Bragg, and the experimental setup is devoted to the Henry William Bragg. So the idea of getting the X-ray crystallographic patterns or the relation between the D planes, here is a very nice story of guiding one senior professor of mathematics, which Henry Bragg was. He was guided by his tinkeringly intelligent son, Lawrence Bragg. So the idea of or the experimental understanding was explained by Lawrence as it is reported by their paper in their paper, and the experimental setup is completely built by Father Bragg, and also the experiment, which sometimes continues even for 12 hours, 17 hours, that has executed by the senior professor of mathematics, Henry Bragg. Right? So this is a very nice example, and at that point of time, Lawrence Bragg has just completed masters and doing PhD in other topic, but he took interest in a new topic, which was X-ray crystallography, due to the different publications from Laue. Right? So that has changed the entire domain of the chemical science, and from the area of physics, now it comes into the people of chemistry, and it was a mixture kind of expression for them. Why? Because it was a kind of mixed experience of shock and excitement. Why shock? Because the long-standing ideas of chemistry is somehow stucking with the results of X-ray crystallography. For example, the people dealing with chemistry at that point of time are very much comfortable with the ionic bond formation of the sodium and chloride, the valence statement, and etc. And when they see that the structure of sodium chloride is something like this, which is now very common to the school students. But at that point of time, it was a kind of shock to the people. And why excitement? Because you can see your molecule. Whatever you have prepared, you can see from the internal structure, and you can understand how the atoms are interacting with each other. So with this journey of shock and excitement, the chemistry world took a little time to accommodate the beauty of the X-ray crystallography. And that time was around us in a scale of 50 years. There is another reason. Because when the X-ray crystallography has started, it was a topic of hard mathematics, a lot of understanding in physics, and probably the people who are dealing with the synthetic chemistry are not very comfortable with the analogy of the mathematics, analysis, and other part. Because chemists are generally weak in mathematics, right? Anyway, you don't have to agree with me. But the thing is, if you see the development, particularly considering the Nobel Prize as a milestone, the X-ray crystallography developed a lot after the Bragg's work in next 50, 60 years. There was a quotation from Tom Blundell, a very renowned crystallographer, that crystallography is great because not only crystals are beautiful, but the people associated with it are also beautiful. Who are the people? If you look at the first era, these are all dominated by the physics. These are the inventions which enrich the field of the X-ray crystallography. The work of Bartla, discovery of characteristic Röntgen radiation, that means now you can really tune the X-ray. If you take one atom source, then you will get a different, a particular wavelength. For example, if you take molybdenum, you will get 1.73. If you take copper, you will get 1.54 angstrom. So you can tune the X-ray, the nature of the X-ray, the wavelength of the X-ray, and by this way, the energy of the X-ray. So this was his work. And de Broglie, who mentioned that wave has a dual nature. So now we can really correlate that why X-ray, being an electromagnetic radiation, is interacting with the electron. Then divide the dipole moment, and then Davison and Thomson, that is the diffraction of the electrons by the crystals. That means not only the X-ray, but if you energize the electron in a very nice way, this can also show the diffraction in the atoms. So now the picture becomes clear, very much clear in 1940s, that it's a phenomenon of electron, and this may be a very nice way to understand the position of the electron, hence the position of the atom. If you look at the second tier, here there is a gap. Black time, that Second World War and other things in Europe where the people are exploring this particular science. And then when the second leg come in, these are completely in the domain of chemists, particularly in the chemical biology. Because understanding of the structure in biology was a very prominent need from the long time. Because if you want to treat something, you need to understand the structure of the biomolecules, and betterment of medical science is dependent on understanding the structure of the biomolecules, so that you can understand the biomolecules and you can properly instigate or start your work to repair them. Right? These are called the treatment. So the medical science has improved a lot with this particular invention. So there was a complete thirst on the biology and chemistry domain. You can see this work of crystallization of enzymes, which is the initiation point that biological molecules can be seen through X-ray crystallography as well. Then Pauling's work about the covalent bonding, Kendrew-Pruch, Watson-Crick. In same year, one in chemistry, another in biology, awarded the Nobel Prize for the structure of DNA. And this was the invention of the structure of DNA is considered as a milestone, that from the pre-DNA era and the post-DNA era, the structural science get completely improved after the invention of the structure of DNA. It was happened in 1950s, but the Nobel Prize come after 10 years. Then if you see, the list continues. Dorothy Hodgkins, Lipscomb, every Nobel Prize is somehow connected with the X-ray crystallography, and the understanding of their final results are somehow related with the X-ray crystallography. In recent time, Venki Ramakrishnan, the structure of ribosome, that was done by Yada Yonath. And if you look at the recent results, that Ben Feringer's molecular machines, the DNA repair methodology, even in this year also, the computational protein chemistry, where the people who design nice proteins by theoretical understanding, their database is completely based on the protein crystallographic data, right? So the computer, to do any work, you are quite aware about the artificial intelligence nowadays. For artificial intelligence, you need to train your system first, right? So that it will give some results. So for any computational output, if you wanted to have a nice results, you need to train your system in a proper way with a lot of relevant databases, right? So the computational, the people who are able to generate nice proteins and structurally modified molecules in biology, they need a lot of database regarding the protein crystallography, and most of the database are coming from this X-ray crystallographic data, right? So it's novel in all way, but how far it reached, this is happened by Jerome Carla and Hoffman. Probably you are aware about the phase problem. Curry has already treated you with lots of this kind of issues. So the phase problem was the major, that bottleneck, so that the crystallography cannot be usable for all the molecules. And that was solved by these two people. And if you look at their Nobel lecture, there is a line for this two person. One is Lindu Patterson, and another is an Indian. He developed a Fourier series. These are the copied from the Nobel lecture of Jerome Carla. He developed a Fourier series which has its coefficient and the magnitude of square of the structure factors rather than the structure factors themselves. These are called the direct method of solving the structure. When you are solving the structure, there is two options coming. One is Patterson method and one is direct method. This direct method is the mathematical formulation of this direct method was constructed mainly by Kedareshwar Bandyopadhyay, who was a professor in Indian Association for the Cultivation of Science, and his name is clearly mentioned in Carla's Nobel lecture. So this is a matter of pride for Indians of long connection with the X-ray crystallography. Now the master stroke done by this person. Probably today morning you heard a lot about him, right? Just died a few days back, probably a month ago in February. He made a radical change in the domain by the formulation of the Selex. And this Selex comes as a window for solving the structures, particularly for the chemists who are not very good in mathematics, right? So this is a very nice interface without knowing the difficult complexity of the phase problem and the complex number, the squaring of Fourier coefficient. Probably you are a little bit puzzled with the reciprocal lattice. No issue. Go with the Selex. In most of the time you will end up with your structure. And sometimes you may need some special expertise, and that has created a lot of openings for the synthetic chemist to understand their structure. And by this way, here are the chronology. It started in 1976 and renovated year after year, 93 model, and now people are using Selex 23 model, which is also updating regularly. Look at the year of awarding Nobel Prize of Zeron Kara, 1985, and the work, 1951. It's a 35 years gap, right? Can you correlate something with the popularization of X-ray crystallography in 1978 by Selex? Because people, by that time in 80s, people understood what is the implication of Carler's work, Carler's and Hauptmann's work, right? When people got a particular, software shoot like this, and by that time, the invention, modernization of the computer system is also coming. So people started understanding the beauty of X-ray crystallography and started understanding the work happened long before, right? So nowadays, with this lot of modular support, the single crystal X-ray diffraction is hard but not very difficult to crack. So what are the tasks? Recognizing single crystal, mounting single crystal, collecting the data, know your files, solving the structure. You are already expert with this, and validate the structures, and finally do a very nice graphics for the good publication. Okay, in most of the time, I reiterate this because in sometimes you may have go with a lot of problems. In 1 out of 10 cases, you may be stuck, but in many cases, you will be gathered the structural information quite easily with this very nice modular effects of the softwares. So now the crystallography has a multi-purpose domain in molecular biology, earth and science, mineral science, solid state chemistry, material science, which is related to the structure property relationship, and X-ray crystallography, which helps to reveal the structure property relationship and how it's give some more information about the structure property relationship. I will quickly go through a few examples of this. You have several domains like supramolecular self-assembly, supramolecular organic frameworks, polyoxymetallics, many things. These are completely, these branches of science is completely, I must say, dependent on the X-ray crystallographic understanding, and a lot of information are coming about their property from the understanding of X-ray crystallography. This is also similar in the series of MOFs. You have a, I think you have a class on MOFs and COPs, and you know what are these materials and what are the beauty of these materials. I'm not going into the detail of this. I'm just showing now a few examples where the trivial ideas of our understanding are stacked, and how you can explain these stories with the help of the X-ray crystallographic results. This is a kind of synthetic protocol of a compound. Don't go with the complexity. This is copper. This is a dicarboxylate bridging ligand, and this one is a NN donor bridging ligand as well. So they will connect in both sides. These are the general story of synthesizing MOF. If you see the structure, this has a square-like 2D layer structure, and these 2D layers are interpenetrated. That means the layers are stuck together. So the beauty of MOF is due to their interstitial spaces, because in MOF people try to do something within the voids. And in interpenetrated structure, as the different sheets are joined together, and that's why the interstitial space are somehow blocked, right? So therefore, when the field of MOP started, these interpenetrated structures are not counted as a very nice findings, right? So, right, these are structurally beautiful, looks very nice. You can see that one seats are linked together with the other, and therefore the space which is used to available in normal structure, these are not available in interpenetrated structure. But what is happening here? Here, from the powder diffraction data, this compound, here you can see at around 100 degrees centigrade, there is a change in the powder diffraction pattern, and you know that X-ray structure can be replicated in the powder diffraction pattern. You can create a simulated powder pattern, because powder pattern comes with the less information, and single crystal is coming with more information. So you can always definitely abstract the less information which is having in the set of more information. So powder diffraction data, which is only the two-dimensional data, that can be extracted from the single crystal data. So now you can see that in 120 degree there is a structural transformation. These are also showing signature in FTIR and UV visible spectroscopy as well, right? And this particular structure showing a 28% of hydrogen absorption. You know the absorption, which is the physical signature of porosity of a molecule, and the interpenetrated structure, which was supposed to be non-porous, that means must not having any particular space to accommodate gas molecule. These are showing 28%, which is a pretty good for hydrogen, because it's a very tiny molecule. It has very less weight, right? So what is the reason behind it? The reason are, I'm not going into the detail with the other gas absorption. You can see that other gas like carbon dioxide and the volatile organic substance, these are also showing similar results. But what is the reason behind it? Then, if you see this particular structure, then with the indexing of the X-ray, powder X-ray diffraction indexing is nothing but getting the structural information from the powder diffraction data. It is not very straightforward like the single crystal data. You need to have some simulation and some approximation, and then you will get some structural information from the powder diffraction data as well. Right? The powder diffraction data clearly indicates that there is a change of space group and the change of crystal volume. What is crystal volume? Crystal volume is coming from the ABC alpha beta gamma parameter, right? That means one asymmetric unit, how much they are taking the space in the crystal structure. So the crystal volume is little bit increased, and the structure showing a breathing effect like this. It was previously like this, and when the water molecules are removed from the structure, the orientation becomes, from this orientation it becomes like this. So the pores are now open for accommodating the gas molecules, right? So these understanding are getting clearly from the help of the powder diffraction data. This is the reason for this higher gas storage, which was not supposed to be, right? So now copper. The previous example was with copper. Copper is, if you compare with cobalt, copper is more coordinatingly labile, right? Because of the Young-Taylor distortion. You have studied in your undergraduate courses that due to D9 arrangement, copper has prone to show Young-Taylor distortions, so that's why copper to center are more labile. But what is happening here? The same thing constructed with the cobalt are expected to be less labile, more rigid. But here you can see that particular structure is going with lots of transformation. That means much more labile, particularly when you remove the water molecule from this base structure. The base structure is very much similar to the copper, but if you remove the water molecule, the structure becomes super flexible, and if you put some other solvent, it will go into a new structure. So it is dividing the basic understanding, right? So why it is happening? If you look at very precisely on the structures, that the supramolecular forces of the water is clearly directing this particular labileness of the system. When you are removing the water, the supramolecular interaction goes on, and the cobalt system are going from octahedral geometry to tetrahedral geometry, and that tetrahedral geometrically oriented cobalt are much more flexible than the copper system. These are the real-time picture of these crystals. If you remove the water, this will turn into blue, and then if you put methanol water, it will show a new structure. Once again, this will new structure, and that will show compound 4 if you carry on the dosing with the methanol water. So that means it's a very complicated story. We took almost 3.5 years to understand what is going on actually. But finally, it clearly indicates that these are the supramolecular interaction which is responsible, and that supramolecular interaction, the understanding of supramolecular interaction, is exclusively coming from the X-ray crystallography. So that means the idea what you are generating from reading these two papers is completely based on the understanding of X-ray crystallography. None other than experiments for the characterization will give you this much information that why cobalt is acting as more labile center compared to the copper. Another example, these are the story for the hydrogen storage. I am not going into the detail. This is another example. A simple reaction looks very, simple. This is another NN donor ligand. This is a dicarboxylate, and this is cadmium. When you mix these three together, it's always a possibility in the synthetic morph that all the ligands may not take part in the reaction, right? So here also we are getting three structures. One is 1D, that is exclusively with the metal and the that NN donor system. Another with the dicarboxylic acid and the ligand. But the third one is a pretty uncanny. Here no dicarboxylic acid is there, but there is a directly bonded chloride, where there was no scope of using chloride in the reaction, right? So how it is coming, that is finally we will come into this conclusion. I will show you how. So this is the one-dimensional structure, very simple. There is a pi stacking and hydrogen bonding interaction which makes this stabilized, right? This is the 2D structure as well. This is also pretty simple. Here the ligand is connected in this way and the dicarboxylate is connected this way. But the third structure, this small tiny crystals, and in this particular reaction, the yield of this reaction is predominant, right? Around 45%, and the other product is coming around 15 to 20%. So if you look at this particular product, here the structure is something like that, and these 2D6 are connected with a bridging chloride. Now the problem is you have not used any chloride during the reaction. What you have used, that is cadmium perchlorate, right? Now what is the source of this chloride? Once again, we have at the beginning we understood that was a mistake. So we repeated the reaction and then made an assay of the other reagents, whether there is a trace of chloride, no other signature of chloride. Then the question becomes bigger. What is the source of this chloride, right? And if you are not collecting these particular crystals, do not see the structure of these crystals, you may not be haunted with this question, right? It is the X-ray crystallography. It is throwing you into a new domain of problem. So then, being a solid state chemist, we went to the mass spectra laboratory, where we generally don't go, right? Then we studied the GCMS spectra, and we found that there is a signature of nicotinamide, right? And then again, the FTIR is also giving the signature of the NH2 group, HRMS, which are giving in presence of excess ligand, it's giving a signature of nicotinamide. So nicotinamide is everywhere. That means in the reaction mixture, there was a formation of nicotinamide. Where it has come? Right? So the production of nicotinamide from imine ligand was confirmed by these studies, and this is confirmed by IR spectral studies also. Right? So there is a oxidation, right? Now we are pretty sure regarding the reduction pathway of perchlorate to chloride. So now it is pretty clear that the chloride is coming from the perchlorate. If you consider about the Latimer diagram and other conservative, chemistry understanding, it is very difficult from that 7-electron transport system, right? From the perchlorate to chloride. But definitely there is a reduction happens because which is supported by this parallel oxidation process, right? If this nicotinamide has not formed, we do not have any explanation regarding that uncanny reduction process, right? We made a standard experiment and we found that this particular ligand and the presence of perchlorate is responsible for the formation of amide, and that's why from this study it is very clear that in case of excess linker, there is a exclusive formation of 1D variant, so we are not getting the results. But in these three cases, we are getting this particular signature of amide, and then the signature of the presence of amide is a clear proof of the perchlorate to chloride transformation, which is coming clearly in the X-ray crystallography results. And the stabilization is so favorable. That particular yield is coming in major portion, right? So what is happening here? This is an electron transfer process from perchlorate to chloride, and here you have the chloride embedded with the 3D MOP. So this is definitely an example of MOP assisted reduction process followed by the parallel oxidation process. So we can call it a framework, might be facilitated the reaction process and holding the chloride. This is an example of oxidation of imine by perchlorate with a metal organic framework support, and this idea of framework support may instigate new ideas in designing some feasible process of important organic reactions as well, where the oxidation reduction process are involved, right? So what is the reason behind this particular thing? We made this control experiment, removing this hydrogen with the methyl group, right? So the labile CH bond is not present, which was promoted this particular reduction process. So here oxidation was there, but if you put methanol, there will be no oxidation. And if you perform this particular reaction with the methyl substituted variety, you will not end up with the chloride containing moieties, right? So this is also the same thing. There is no signature of the nicotinamide in the reaction mixture in mass spectrum, as well as ESIMS spectra as well. These are the trivial structure of these two compounds, very similar to the previous one, but not the chloride containing structure. Right? So these are the conclusion or the take-home news that particularly for a chemist, the single crystal structure is not only a tool of structural characterization, it always gives you an insight of the structure, sometimes the chemical process involving within the structure. And in most of the cases, it will fertilizes some of the ideas, giving new ideas regarding the chemistry, what can be done, some new understanding, some new results, and you can really plan your new ideas from the results of crystallography sometimes. So if you have more interest, you can go with a review paper where we have discussed many similar kinds of examples where the chemistry started from the X-ray crystallographic results. The DOI is given there. So that's all for today. Now the podium is yours. Please comment. Thank you.
So do we have questions from the audience?
Everything answered?
Maybe we should give them some time to construct their questions as well.
Yeah, okay.
Their doubts.
Please. It is still under construction. Yeah, okay. If you have any question, you can mail me anytime. I think email ID will be also circulated to them.
Okay, if there is no question, then join me in thanking him.